Ooh. 1, 2, 3, 1, 2, 3. Let's get this
You're
off.
going you're going to give that speech again for
Oh no.
Sorry for those online. I really apologize. Basically, I'm TJ. I'm from outside the group. I've been coming here for better part of a decade and really enjoyed this group specifically for the knowledge and conversation we usually have. Past that, so big thing with this paper is I know that it's very long. A lot of the appendix sections was more zero shot to few shot learning on this specific model. But there's been a lot of updates in the last year and a half since this research really was developed and pursued. So would love to get your ideas and thoughts. And if you have questions, I have the paper pulled up. It's been a long week. I've read the paper a couple times, but I'm by no means perfect on every little nitty gritty thing. I'll help where I can. Big thing for authors. I always like to touch on authors. There's quite a lot of them. They're coming out of Zurich and Warsaw. This is around the same time that ChatGPT 3.5 was out for context. And so there's been a lot of differences in thinking about how from prompts to the actual ingestion of the data to the output has been sort of conceived and thought about. So just to give a little context of that. During the presentation here, I would like to give a little overview of sort of what I've just been doing, why this might be interesting. I pulled all the tables and graphs from the paper, trying to dissect them a little bit more as we go through this presentation. They had a couple example prompts. I really like the format of the graphs on this paper. It's very color-coded. There's a reason why it was a top paper at AAAI. I have a bunch of skepticism, and then kind of go through some of the updates that have been happening in this last year, and then discussion from all of you. All right, so really, what is the big picture here? So as a lot of this is saying, it is prompt reasoning schema, where there's either like the single chain of thought that has been sort of initially started to multiple independent chains, to really a tree search that might be interesting to think about as you are generating like prompts or a dissection of what might be similar when you think about that. But where this research kind of goes a step further is they added an arbitrary directed graph or a DAG for these thoughts, where they're going to generate candidates, they're going to aggregate, and then they're going to refine on an intermediate step with loops. Operations really, some of these trees don't natively support. And so the big thing here up in the, I'm not gonna, but the big thing up here in the right corner with the schemes, the big 5 types of models that they're comparing against is this chain of thought, self-consistency, thought decomposition, tree of thoughts 1 you should think about, and then tree of thoughts 2, which is just another larger model that they have for the types of trees that they're creating.
From the same group or those are different papers?
They're all over the place. I believe 3 of them are more like the tree of thoughts, I think is from the same group, coming out of Warsaw. But the chain of thought, I think, was the arbitrary one from like 2023, which is probably research from 2022, and more like ChatGPT 3.5. And so really what the top right corner is trying to show is just a nice little example that has a bunch of different little acronyms with question marks here. That is just SC is single chain of thought, MC is multiple chains of thought, TR is tree of thoughts, and then AG is arbitrary graphs. And so they're just trying to give reason on why this is even interesting in the first place, and sort of where it is combining all of these concepts into this single aggregation model. And so with this plot here, this is sort of the diagram of their ideas of how to compare themselves against everyone else. They compare the different schemas here, and really most of these prompt engineerings are either any of these things, but those structures really don't let partial solutions feed back into earlier steps of the graphs, which really results in different branching as graph of thoughts really generalize the control flow of these DAGs. And so their steps, just as I said here, generate, aggregate, and refine. And so this is really a control flow upgrade to prompt reasoning. And that's sort of what we should take as we keep going. The trade-off here, they have a latency volume argument that we'll get into, where the trade-off really is score dependent. And this is sometimes arbitrary jargon here, but it's sometimes via self judgment with the LLMs. And then the unknown gains is really the reasoning trait models. And so let's go ahead and get a little further into this. Really, the core idea here is that it's representing this graph where we have the vertices and the edges, where the vertices are thoughts and the edges are more encoding dependencies. And so it provides a really nice set of operations for the graph where they have to generate, aggregate, improve, refine, and then they score. And then they have this concept called keep best, and that's just their selection of these arbitrary trade-offs. So really, the latency to volume trade-off is what sets them apart from a tree of thought. And so here, latency is the number of hops of a final thought, meaning as they navigate down the branch for this prompt, they sort of either aggregate, they trash part of the graph, and then they reconfigure. And so it is the volume of how many prior thoughts could have been influenced by this prompt in itself, and they give sort of latency and volume computational limits or theoretical limits that they have produced here. Because the aggregation really lets information cover many parts, it really reaches the final model in a faster time due to the volume that they choose. I'll show examples that they have later on from some of their prompts using either sorting, they have merging of NDA documents or non-disclosure agreements, much more text than anything, and then they have a little bit of massive aggregation of numbers. All right, so their model really has these two different distinct operations, the static graph, a template of the task where they have a split to solve to subparts to aggregate and refine. And they have then a dynamic state where it sorts the concrete thoughts, has a score, and then the candidates that survive are the keep best. And so really from the graph theory view, they're basically aggregating all of these inputs into one sort of object, and then the generation of these vertices through an edge of model dependencies. For the example that they have sorted here, this is going to be arbitrary number of strings and number of lengths for just sorting numbers. Very simple task, of course, but they're able to start to merge first, take this merge, and then they split the into subarrays for subsequent sorting. So as you branch out, they're merging and splitting at the same time to see how fast and efficient they can. One thing I'm just thinking out loud right now, I probably should have thought about this ahead of time, but just for different sorting algorithms, how does this stack up? Or is this just like arbitrarily doing a bubble sort or merge sort? I don't know. So that bad thought out loud. But with the writing task, it's very interesting because then once you throw on sort of this NLP piece of doing more scoring for words and arbitrary strings, they are doing a more complex task on trying to understand how information might need to get sorted via arbitrary NDA pieces, different types of sections of the articles itself, and then aggregate that into a better output for what they have adjusted. So this is going, I am not updating with the screen. There you go. It is. There it is. Okay, sorry, just a larger picture here. This is a full page of graphs. Just show of hand, anybody actually get to skim the paper beforehand? Okay, I know it happens. It's been a long week and it's a Friday, so this is actually one of the better figures that I liked in this paper. It was a full page, and I think this is one of the reasons why.
It's super dense.
It is super intense. This is only half of the page. So the next slide will be more examples that they have. But really what they're trying to do, and it's not that complicated because they have the legend up in the right corner. Really the architecture overview is going to be the 4 different pieces that they have.
You can use this to point if you want this for us.
Yeah, you got it. So really the legend here is basically all the different things that they have. They really have 4 different pieces to this model. They have the prompter, the parser, score and validation, and then any kind of like human feedback with the controller. And so really it looks a lot more complicated than it is. But these are just the 4 different pieces of the APIs that they're calling as the information is flowing through this model. So for the API with the controller, they're just having their different parameters, the cost features, instances of all of the different pieces within this model. Applications really with, I think this is graph of objects. But this is just another piece where they're trying to maintain the scores that they're getting as they're aggregating and generating at the same time. So it's just another little piece that they're calling scores from. How they do this is probably just a SQL database that they're just calling back and forth and probably doing something smart on a supercomputer. Apps for APIs for the prompter. This is again just a bunch of different calls that they have that they generated a backend script for. So these are just things that you can call and put in your code, as they were really trying to make this more accessible for people to use outside of this paper. And then the API for the parser is exactly the same thing as above. Architecturally, the view is they have the controller here. User's going to be putting something in. They're going to have an LLM specific thought of transformation, so it can be any kind of LLM that you want to put in there. ChatGPT 3.5, a Llama, an Olama model, or anything you can kind of bring from Hugging Face, easily throw in there with as many billion of parameters as you want. But this graph of operations then starts to do the reasoning state. It has a ranking using a harmonic scoring algorithm. I didn't put any of the math in there. It was a little bit loose, in my opinion, for how they set up with the math and how they arbitrarily chose some of the things. But the goal is really to indicate the top scoring thoughts, especially as they aggregate and generate. So as the user goes through there, this controller will then have a prompter to an LLM and have a parser come back through. This thought, I think, is a terrible way of delineating things. Brad, you've talked about this a lot. But it anthropomorphizes way too many of these programs to basically say it's a computation. It's not a thought, it's a computation. It's a function approximation of data that we're just trying to better tune.
That's what I kind of wanted to interrupt because I get very confused with these graph reasoning for LLM papers because we have a language model that is just a language model, maybe with reinforcement learning on top for some certain kinds of actions that the model can take. But sort of what that reasoning process is formally is lost on me. Like what it's not, these things aren't doing, reasoning as you would encounter in a formal logic class. They're just kind of
they can.
They can. Do they? Is that rigorously defined now for they can do it, or are they just doing it by avenue?
Well, the thing is, language encodes for programs. When you're going through a language sequence and then you say but, that is doing something probabilistically to the distribution of text afterwards.
Sure.
And the LLM can learn to inject that into different parts of its trajectory. So like in a DeepSeek paper, the model will learn through RL to be able to reflect on its own trajectory and course correct if it suspects that it's wrong. And if you look at the probability distribution of the token space, it's actually very high complexity at that exact token. And so there have been people who have this project called Entropics. They used a very fancy sampler to use the complexity of the current token as a sampling mechanism. And you can insert tokens that were correct for high complexity. So, but maybe entire sequences, like maybe try re-looking at your trajectory and see what happens. And you can actually get a baseline improvement by like 8% on math benchmarks.
Cool.
And so even though they aren't, I think thought is definitely like over anthropomorphizing, but like computation is under describing it a little bit, I think. They are doing something that is similar to us. It's very alien, but it is something linguistic.
What I was going to describe it as is what you've characterized, I think, correctly as is linguistic reasoning.
It's a linguistic reasoning,
which is different from formal logic. There's a reason that formal logic abstracts away. You have propositional logic and these things away that are not natural language.
Yeah,
they can be. You could try to encode natural language to these, but they're not one to one.
Well, that's the best part about them.
they become even easier then for an LLM. When
Yeah.
it's just a formal symbolic manipulation.
It's better that they are a fuzzy system than formal logic, because formal logic systems cannot reason about themselves very easily. Like SAT solvers cannot prove even stuff like addition commutativity. But LLMs can trivially prove that in whatever language you want. You can invent a new system of naturals and you can apply that, and they will be able to recognize a pattern and prove that for you. And so part of the fuzziness of it is also what makes us so powerful, is that we aren't stuck thinking only in the formal language. We can also think in terms of this fuzzy linguistic language. And the LLMs can do that too. They can also use our formal tools. So I can plug a lean into it or plug a SAT solver in, and it can use it in the same way that we can.
So then, to my question of what these links tend to be between, thoughts or whatever however you want to characterize them, states, whatever you want to call them, are they typically formally characterized, or is it as vague as there is some kind of encoding relation, and that's like, and I have no, I just disagree.
Yeah, so maybe we can get back into the graph of reasoning state here. So even just looking at the legend here, there's three different kind of symbolic reasoning things here, all kind of nested into this graph of reasoning state. Even if we take this beginning thought state that is kind of coming out, let's say maybe I don't know, if we have an arbitrary sentence, it's going to take part of the sentence, have context to it, maybe there's multiple parts to it. It's then going to have this thoughts or the edges here, where it's going to have a thought state plus its thought score. This is going to consist of really incorrectly including missing pieces, duplicates that might happen, or positive scopes from the components of the initial thought state. These will then have associated operations as they keep going, and then it's going to start to ablate the graph based off of the prompter and the parser. And that's where it's getting a lot of these scoring plus thought state back through the LLM into the reasoning graph as the reasoning graph iterates and updates. So this aggregate and generate is happening within the graph reasoning state. Does that help a little bit?
I don't think it quite answered my question. I think maybe you're saying that at least two of the kinds of edges you could have are these, take a problem and split it into subproblems, and then or take subproblems and aggregate them into a full problem. Is that the only kinds of links that they define here? Is that universal across these reasoning graphs? Like that's or
Yeah, that's a great question. Here, let me go to the next slide.
You specifically had a previous slide where you talked about the links, and I was just like, I wasn't sure what it meant.
Yeah, so this is the second half of the page that I was talking to you about. I guess, yeah, they're omitting some of the stuff with space. But let's take 2, for example. So I here is just giving this example of the generation of thought graph that we were just talking about, and sort of how it is either branching or not branching. For a prompt used by t of k equals 1, and then it repeats 4 times. So there's going to be 4 different aggregation steps going from the parser to the back to the graph. And so I believe in this example, it's sort the following lists of ascending order. Output is a sort number of lists, no additional text. So input, it looks like it has, yeah, just this string of numbers where it just has k of 1. So the example is just 1. The output is then the sorted list. Yeah, it looks like it is. I'm trying to rapidly read the text. This is a lot of text on this page. I'm sorry, everyone. But perhaps if we have this list, for example, what's that? It is going off the screen. I apologize, you guys. The prompt, there it is. The prompt is using an operation generates the branching factor K4. 4 new thoughts are constructed based on the LLM's reply and prompt. So what is that saying? It's splitting the list of 64 numbers into 16 numbers each. The first list should contain 16 numbers, second list on and on and on. Only the output of the final lists. Okay. So it has the 4 arbitrary lists, then it gives an example, and then it's still going again. But I guess you're right. I'm not certain on how it's either scoring it or then reorganizing.
Well, so maybe go back to a couple slides ago.
Yeah.
Because there were
This one.
I think even one more back.
about the.
Yeah, okay, no, the next one. It was the one you were just talking.
Yeah, no worries.
So edges and code dependencies. So that's what I was asking, like, what does that mean? What is a dependency? And so maybe this set of operations is that's just the different kinds of edges that they have in this graph. Is you can have different, like it's this generate, maybe it's branching or a subproblem generation. Aggregate is a merging operation. I don't know if that is like reasoning in my mind, but whatever. Improving, refine, scoring, and keep best. Again, I don't know. Like these, like are those are just the formal operations?
These are different operations to perform on the context of the LLM. So I've personally tried like messing with these things. I found most of them to not actually be that wise of an idea long term, because half of these operations destroy the continuity of the trajectory, and so it immediately invalidates it from being used in RL.
So meaning there's like going to be drift as you have different contexts.
It's not necessarily drift. It has to do with if you are, say, like the refining stage right there. If you do a refinement and then you continue the trajectory from there, what is the trajectory, right? Effectively, when you are doing a refining step, you are forcing the next iteration to continue from a different context than it started with. But to be able to do RL or any kind of learning mechanism, you need it to have continuity with the original condition. Right, so you need that continuity and that.
Oh, but there's a path that you trace from start to end, right?
It's traced in the framework. It's not traced from the perspective of the LLM. The LLM has a discontinuity right there. The context goes from beginning prompt to right before refinement, and then from refinement to the end of the problem.
Oh, but then yeah, it's
right. You can't stitch those together because those are two completely different probability distributions. And so if you were to try to use this with an optimization algorithm, it will break. It's extremely brittle. I've tried those so these things work very well if you freeze the LLM. If you like conclude this is the best LLM you'll ever get, and you won't try to do learning, this actually works very well. A lot of the agent frameworks that I've interacted with use this. But I've seen recently that all of them have been shifting away from it because they realize, oh, RL isn't actually that hard. Let's just design it to work with RL in the first place and let the learning take care of it by itself. And so we see the shift from like early Cursor and the early Asian companies all did something like this. They all have these fancy like scaffolding and context manipulation techniques. But the more sovereignty they gain in how they can like just the fact that they can use their own models is the first part. They start designing it in such a way where they can do learning later. And then once they have full sovereignty, you look at Claude Code. Claude Code is a straight line. Like in terms of the flow, it's a straight line. Codex, also straight line. And even stuff like subagents. Subagents are actually fine. Subagents look exactly like tree of thought. You can span off like that, but there is still continuity in that trajectory back to the base station or back to the base starting condition. So you can still do RL. Yeah.
Okay. I'm gonna skip out of the red slide that we just had. This is some of the results they have and maybe is a little better on trying to explain what is happening in these examples. So graph of operations, trying to sort these 64 numbers, I think highlighted from the text with red. Here they are decomposing the sorting and using the graph of thoughts and the operations with generate, aggregate, score, and keep best are really described here, where they have the graph initially. They generate sort of a different subset of suboptimal operations here. They score these and then start to arbitrarily choose what is keep best and then aggregate, score, keep best, generate, score, keep best, and then this is going to keep going until they have some kind of output based on, I think, the depth that they're trying to do versus the number of operations or the number of refinements that you're trying to do. So in this detailed example, they have 64 numbers splitting into the 16 chunks. Each of these 16 chunks will then have a generated score. They will then go into the best one here, sorting implicates within the generating stage, assess how each sequence is scored or sorted. And so how well did they do from 0 to 9, they get a different score. 0 indicates correctly solved to show the higher we do a maximum score. So this is still a difference here where they have maybe these 16 numbers are all sorted, so if it's 100, these 16 numbers are worse, so they only have 86, and they keep the best scored thoughts, so it would basically be the path coming from left to right here, and then they just keep iterating and iterating until they have their final solution where they merge everything back together. And if I let the screen pause, it'll show this final block at the bottom. There we go. So here it keeps the K of 10, means that they try 10 different aggregations on the 2 inputs of the 16 element subarrays, going into the 32 by 32s, and then they merge into the 64 by 64 array. This is kind of what they're doing with the graph of operations. I don't know if it's this.
I somewhat don't like this baseline, mostly because the model is, whatever model you use is going to be heavily already conditioned on what a sorted list of normal numbers looks like.
Yes,
I would greatly prefer they use like pure symbolic and give it like a list of partial ordinaries or something, and have the model reason over that.
Ooh, yeah, that's
Yeah.
fair.
Right.
And I think that's why they were trying to do NDAs, probably because that's just what they had.
Yeah.
Because you're supposed to only get partial information.
Right, because my sense is that for a problem like condition, the problem that's so conditioned in text, like a normal list of sorted numeric numbers, you could just make a model bigger and then pass in a gigantic list, and it will be able to sort that. Because if you're already going 0, 0, 0, 1, 1, 2, effectively the task is no longer sorting; it's counting how many instances of this number is and just putting it there, and that's it. Because once you're at 1, and there's 2s in the original unsorted list, you just put 2 there.
Yeah.
And the next number is the other 2, and then you do that until you run out of 2s.
Yeah. Okay. Well, let me keep going and give a little more context of why might this be better in a bigger picture. These are 4 different graphs they have scattered at the back of their paper. Here, what we kind of need to understand is the takeaways is going to be cost versus effectiveness. And so there's always a kind of this understanding of if we're using like chain of thought, if we're using trees of graph, if we're using graphs of thoughts, what is the cheapest option as we're doing prompts and sort of generating this either the same information or different information. So there's always a cost component involved with this. These are very messy graphs, so I apologize that it's also very thick, but for the big takeaways here, there's a consistent pattern throughout that when the task can be decomposed and then recomposed, graph of thoughts improves quality and often lowers matching cost versus tree of thoughts. So here they have 100 input samples. They're using ChatGPT 3. Llama 2 was trained, but it was slower and performed worse. So they just excluded that. I think it's in the appendix, but it doesn't matter. They keep a temperature constant at 1.0, and they use about 4K of example context, which is able to compare against all of these variants. Trees of thoughts uses here a higher branching factor of K and a lower depth of L. Train of thought 2 would use a lower K, higher L. And I think that's just the difference there, just to contrast what they're doing with both depth and number of samples. And so the graph of thought advantage hypothesis is that it decomposes the problem into solvable subtasks, scores, keeps the best, then aggregates, and then can predict and improve quality with lower cost than is compared to tree of thoughts. Figure 5. So these are the first 3 graphs here. The error counts in the sorting, they have 32, 64, and 126 elements across the different models here. The bars also show the total cost per setting. Takeaways of these are that graph of thought consistently beats the tree of thoughts, both in error rate and at lower cost. By how much, it looks a little arbitrary, I'm going to be real with you. That is one of my issues, but why this helps is that the graph of thoughts yields a better fidelity or frequency aware scoring and lets the graph of thoughts discard weak partials before aggregating. Other things that might be interesting, the benefits here, growth with the problem size, as the graph of thoughts too, where there's a lower K and higher L, or more depth and less samples. There are around a 61% improvement and a 69% improvement on a median error. This next set of graphs, the next 3 here, this is the error counts for computing some kind of set A intersecting some kind of set B under a various number of sets, 32, 64, 168 with overlaps. And then it also has total cost as well, just like we were talking about. How it's scored. The error scope is extras. That's nonsense. I don't need to talk about that. Basically, the takeaways. It's encoding scoring. So rapid thought really drives errors down while staying below tree of thought's cost. So really thinking about sort of these blue graphs, even though that there are very similar outputs in sort of how they are finding their errors, the cost is lower for graph of thoughts when using each of these sizes of models. And so that's really their big driving point. I think what their selling point was, especially in the abstract, was the cost per computation at larger scales. So does that mean that we can have a lot longer strings that we can then iterate for? Maybe. I don't know.
Do they detail how they calculate the cost? Is that just API costs?
Yes. So errors. You know what? I don't know. I'd have to pull up the paper. I'm sorry.
Okay.
My guess is that it is API costs. It has to be API costs.
Yeah, my sense is that that doesn't sound right. The most efficient should be chain of thought, and the second most efficient should be tree of thought. Mostly because of prompt caching.
Yeah.
Yeah, right. Because we've
Yeah.
already indexed everything, and so the next generation is going to be incredibly cheaper than everything leading up to there, versus the graph approach forces you to re-index and validate your cache every now and then, which should make it cost more. That's my sense.
Bottom two graphs, I'm going to be honest, I don't know as much as the other things about it. I know that the bottom left-hand corner is trying to plot the cost versus errors of a couple different types of graph of thoughts that they had. They call it graph of thought 4, 8, and X. They're different passage split strategies. So in these graph of operations, I believe it is just how they are splitting more arbitrary symbols or the language itself. And so the text is split into different passages. Its count per passages are aggregated. Scores are then summed by divisions across keywords. I don't think it's important to really go over that. And then the final one is a 10-point quality score. It's the harmonic mean of redundancy and information retention, judged by an LLM multiple times on average. It seems like a little horse before the cart kind of an issue, because they're using an LLM to judge the LLM.
Wait, those scores are scored by the LLM.
So yeah.
Yes. It's okay. I think they needed to do this to generate better with the problem of using NDAs, and so I don't know. The takeaway here is that it achieves a higher score quality based on the metric that they chose at an acceptable cost, aligning with the claim that aggregation of sub results is easier, so more robust than end-to-end aggregation. Fine. Let's go to the limitations. We've been talking about this for a while. So the evaluator dependence. So really the two tasks, they need to be crisp. The problematic scores, really the sorting violations, set error counts. Document merging really relies on LLM self-scoring. So this snake eating its tail problem. And there's going to be
bootstrapping works.
What?
Bootstrapping works.
Yeah.
Okay.
Yeah.
It's like all feedback systems work like that.
But yeah,
I mean, it can sort of collapse, but it can diverge, but it can stabilize.
No, you're okay. So you're absolutely. Let me not be so naysay. I won't use the analogy, but yes, drift can really happen. Anchoring on phrasing or more common phrases or different types of sub operations will come to light a lot more, and so you don't have as many edge cases that will be able to help refine over time.
You just need to add another control loop on top of it, and then control that with another control.
Oh,
and yeah.
Just one more
Until you're
scaffold.
tired.
Just one more scaffold, and we'll get to AGI.
Yeah.
Well, look at the biology. That's how it was built. Through scaffolding.
Yeah.
Redundancy of the feedback loops.
But yeah, another thing we've been talking about is the model converge. Results really rely on these older model classes, which there are weaker performances on some of the like llama models they were talking about or different things. We've been talking about modern RL approaches, and the generalizability to today's stronger reasoning models isn't really established in this paper. So I know that this paper has now been cited 1,200 times. So even in the bloat of LLM research, that is still a decent amount. Um, but it's just interesting to note that I didn't get into the citations of what was most cited
How
from
many of those
things that
papers are
cited.
cited by LLMs?
Ooh. Okay. And then another thing that we really were talking about too is task fit. This task is very easy. Sorting. It's something we've known in computer science for a very long time, and the efficiencies, quite a lot of different sorting algorithms. But then taking arbitrary symbols or even mixture of information, how does that
It's a
like?
poor example of reasoning, like you said.
Yeah.
I think, yeah, much
Yeah.
better example could have been chosen.
Well, and especially when thinking about how natural language processing isn't just a discrete ordering model. There's so much complexity with it too that it really waters down the problem to just something. But it is, I mean, someone has to have a baseline. But
I maybe wanted to ask about this kind of design, and you suggested that even in the more contemporary work that this idea of breaking up problems into these subproblems that you had to subagents or whatever
Yeah.
is still quite universal.
You have to select it extremely carefully. They pointed out, if you go back to the previous slide,
yes.
that line right there is a glowing red flag. So for tasks with non-decomposable objectives, or
That's what I was
constraints,
yeah.
that one is scary because most problems do not behave like this. Every programming problem in most programming languages do not behave like this. You have a bug, you cannot decompose a bug into multiple bugs and fix them. It's usually very global behavior. Only some languages have this behavior. Lean has this behavior. Like the formal proving languages, you can actually decompose a unproven theorem into multiple lemmas and then independently prove them, and you combine them back together.
Sure.
But this is not the same. You cannot do this in, say, like a debugging session or like a writing task. Most writing tasks do not behave like this. No writer clones himself 3 times and then writes 3 different books and then combines them at the end.
If I could have myself write my introduction, my method, there would be best.
We decompose everything.
Not well. So what I was going to say is that I think there are decompositions potentially. I don't know if they're always as easy as breaking into sort of discrete chunks. There's harder questions about how to choose those chunks.
Yeah, but once you choose them, that's it. You're working on one chunk at a time. There's single tasking, everything.
Sure, but I do. There
It's
are
realistic.
non-decomposable problems and global problems as well, like systems that are highly interconnected with their subparts, and as soon as you adjust one subpart, all the other subparts are affected, right? So there are, if you could break up a system into independent subparts, that golden.
Weakly dependent. There are like
Yeah.
more dependent versus less dependent, and you can work on. Like those are strongly connected, so you work with them, but you're only weakly affected the parts, and then you can converge maybe.
In a numerical context, I think that mostly works out because like most operations with work is like algebraically very associative. So you can decompose things like that, but once you diverge a little bit from that space into things that are a bit harder, like bugs is a huge one. Like you look at a bug, it's usually not where the bug happened. You have to trace through the entire code base, and sometimes you have to refactor the entire code base to fix that one bug.
But the way you do it, trace is the key word for you. You look at this submodule and you find how the bug enters there. Okay, you're done with this submodule. You know that it came upstream. You go to the next submodule and you see if it originated in there or came.
But that's inherently sequential, though.
But it's modularized. I don't like. It's still, you don't have to see the entire thing at once.
Yeah.
No, but the hard part is that it's associative, but it's not commutative. So you have to by yourself trace through every single step along that. So it's
not parallelizable.
Yeah, so it's not parallelizable. You can't do something else in composition.
Oops, sorry guys. Let's wrap this up. I know we're getting closer to the top of the hour, but give a little more relevancy. I know we've been talking about how this was done more likely in 2023, where there's a lot of different schools of thought. ChatGPT 3.5 didn't necessarily have reasoning going on. Trees of Thought just came out as a baseline search for partial solutions. Just to give a couple of papers that I was able to glean that were like most cited. Self-discover, instead of hand designing operations, it's trying to self-discover intrinsic tasks. So learn structure versus this graphic thoughts engineering plan is kind of the good analogy that I was finding from different blogs. Structure guided prompts, I'm not as sure about that one. I don't have as good of understanding about that one. But reasoning RL models really came into fashion this year, especially with DeepSeek, OpenAI o3. I think especially this group has done a lot of work with DeepSeek just because you can get in the black box of everything and see how it is actually thinking.
You're not allowed to download DeepSeek at GSU.
Okay.
Really?
It's one of the banned softwares.
Because it's yeah.
Yeah, if you go to the website, you'll be flagged.
On a non. Oh,
You go on the Hugging Face website for DeepSeek or the
I don't know. The
Yeah,
Hugging Face
DeepSeek
is
is
probably-
everywhere. I mean,
Yeah,
but it's on the list of banned software for GSU.
interesting.
They send
That's
us
'cause-
an email every week. You're like, don't use DeepSeek.
Well, DeepSeek the website or DeepSeek the
I think the website is.
Okay, that makes sense. Because like the model, if you host it on our cluster, like what's the problem?
They would.
oh no, they have fears with that.
I would spread the word.
I heard
This
in,
is not
in
as-
today's
as it's-
A16 in today's A16Z podcast, I heard from them. It's like, oh, what if China inserts something into the weights of the model? Like open weights models are bad. And I'm like, oh my god.
Interesting. Well,
Yeah, they fear like I mean
yeah, combining that with the previous ACZ talk with the White House, consider talking about banning math, makes me kind of.
no, but like that was like what are you talking about? It's like only good open source. Like some all animals are equal, right? But only like some animals are better.
So great.
So really, this is end of the day. Sorry, no, yeah. End of the day, the graph of thoughts is just trying to help with the complexity of prompt time search. May not be as great as natural merges and cheap evaluations. Are not really true. So unless there is this arbitrary idea that the natural merges are cheap for evaluations, graph of thoughts will remain clean, but stick with RL. It's a lot easier to train and understand how the reasoning will go.
Yeah.
Especially as we've been talking about. And I think that's the big takeaway of this is a great understanding of what happened a couple years ago, and understanding sort of the growth of what LLMs are doing is important, and not just knowing what the best is. And so that's why I thought it was important to try to go through a paper like this today. Sort of like understanding chinchilla scaling, understanding sort of where GPG even came from, BERT, for example, understanding those little pieces, and especially as we grow with natural language processing, the history is also important. So that's why I thought this was a great paper. I don't have much more than this, other than we have about 10 minutes if there are other questions or any kind of discussion.
Well, I have a comment about DeepSeek and all of the models.
Yeah.
It's like all of the models that are running in the cloud potentially bad because you're giving up your freedom, your data to you don't know where.
Mhm.
Right. So, but the models themselves, if you're running them locally, I don't see a problem with that.
Yeah.
So.
I wish Wittgenstein and Dummett were allowed to see how much linguistic reasoning has sort of shined. There was
You saw it coming.
Well, yeah, there's been a long history in the philosophy of mind and saying that linguistic reasoning sort of isn't proper reasoning, that it's sort of a model for how mental reasoning happens.
Yeah, I mean, like I think I would actually love to poison the well completely on using these words like interesting, novelty, and reasoning. Like I just want people to stop using these words like completely, just because like, what do you mean by reasoning? Like when people say when mathematicians mean
I mean, like deductive reasoning is like formally defined. That's what I mean by reasoning. Or like inductive reasoning is also formally defined in formal logic, and that's what I mean. I mean, reasoning in natural language, again, because it's natural language, could mean 5 different things, but that's what I mean.
well, the models can obviously do induction though.
Formal logic is much easier than what language does. You don't even.
Yeah, but even then, language models can do inductive reasoning. You can give them an inductive process, give them a problem, and then they will be able to follow through those rules like pretty easily. Not reliably, but neither can us, because we're inherently fuzzy systems, which is why we embed points of formal like verification along the line.
Yeah, my point wasn't to say that the LLMs aren't doing reasoning. I think that got misconstrued. It's just like the difference between what's happening in terms of reasoning with language in the philosophy of mind and formal logic has been differentiated from other kinds of reasoning. And I'm not saying reasoning in the loose, whatever, 1,000 neuro papers say their models do reasoning
Uh-huh.
sense, but I'm talking about the history of philosophy and reasoning, philosophy of mind. It's, there are ideas of, what we are doing when we mentally reason through a problem as well. And if that maps exactly to, what is happening when we reason through something linguistically, and if that's, what these models are doing, I think what these models are doing is something altogether different from what humans do.
Yeah.
And so it'd be nice to think about that characterization, formally and think about what it means.
Yeah, on a related thought, transformer circuits, Anthropic, Haiku, they did actually look inside the model when doing addition problems, and they did actually find a subcircuit that actually does do addition. Like you can actually extract that out and use that as a calculator, and you can do small integer addition on that circuit.
Okay.
Yeah. And the nice thing is that during training, what you can do now is freeze, if you can find where that circuit is, you can freeze those weights. Just do a mask with on the gradients.
Is it emerging from like multiple different types of trainings, or is it just like the one model that they had that they trained up? I don't know. Does that make sense?
But it's not a real algorithm, right?
Because well, I'm saying like we all have different
It's not general
experiences.
for any length integers, right?
Yeah, it's not general length integers, it's for small integers.
Yeah, but then it's not an algorithm. Then it's like the kids learning first, like just
Principles.
But we don't, but like even our
but then no, well, a lot of my addition is not an algorithm. It's memory and
Yeah.
combination.
Yeah.
But I know a formal algorithm, and then I can just sit down and do it, and I can add any length integers just following that algorithm.
Yeah.
Even
So addition's a very interesting example for the reasoning discussion as well, because you say you find a circuit that's like an addition circuit in a computer where you can just plug a number in and it will do that kind of thing. And I wrote my thesis on an undergrad, and there's a big discussion in the philosophy of math and math education, as well as when people do math, are they doing symbolic manipulation entirely? Is that all that we're doing? We're doing mathematics. It's all the reasoning that comes into mathematics. Just
no, there's a lot of geometry in my brain.
Oh no! I disagree with that. It's a line of thought, right?
Yeah.
But and I think we have with these models an interesting opportunity to ask these really unique questions about what reasoning actually is.
And on the frontier of like philosophy, I think these models are exactly where people should be researching, which is why I'm sad there aren't more papers in like literature and philosophy.
Well, I think everyone's concerned about the ethical implications. A big part about a lot of the philosophers are talking about that.
Yeah.
Even there is no ethical implication. Torture this as much as you want.
Well, they're talking about like the companies usually that are behind these things.
Oh no, but like that's you download the local model and
Sure.
Or like what's the complexity of a brain that we actually care about? We use mice, rodents,
Right.
chimpanzees got docs from NIH. What does emergent actually mean, and at what scale can we actually have all of these? I don't know. There's also an energy issue and like an environmental issue as well with this that nobody talks about. I've been trying to get people to talk. But
everyone's talking about the data centers.
Well, people are talking about data centers, but like they're talking about the wrong thing with the data centers also. They're talking about water usage, but
can I mute myself? Am I out? Should we stop? I have a very wrong thing, but
by the way, what Mike said he downloaded DeepSeek. That was a joke.
I never download DeepSeek. I'll only use organic American land.
But yeah, no, there's been big fights happening right now in multiple cities that I know that there's bad actors and a lot of bad faith happening right now trying to build a lot of these data centers, and it is hurting people who don't even understand what's going on.
The problem is that people don't understand that anything they type into the website goes out.
Mm-hmm.
And
or nobody's really even done the noise pollution for any of these data centers and how it's disrupting habitats and agriculture, and beyond the fact that we're using energy water in areas that shouldn't have that happen, specifically Tucson, but don't worry about that. I think we're getting close to the hour.
thanks. That was fantastic.
That was a great topic.
Yeah. Very interesting.
Yeah, thank you all for contributing. I know it's very rare that I'm out here, so it's great that I happenstance was able to line up with my schedules and everything. So
Yeah,
Thank
yeah.
you.
So you got a faculty position at Tech now. Are you going to be in Atlanta for the time being? or
not
what's-
at the moment. I'm able to teach online, which is
Okay.
great.
Gotcha.
Until they have a demanding return to work order, we'll figure it out when we
I was surprised. I thought it was one USG wide.
It-
The disorder.
so record.
We should stop